Hello, and welcome back to the course. So today we're going to look at the argument, trying to define the argument for a complex number. And we're going to look at what the exponential does to the complex plane. All right. So last time we said that if we write a complex number in the polar form, so r e to the I theta, then the theta should be the argument. So maybe we can try to define arg z, giving the argument, just so like we have modulus, so we want to have argument as well. Well, there's an issue because, well, if theta is an argument, then theta plus 2 pi gives you the same number, as does theta minus 2 pi or theta plus any multiple of 2 pi. So really, the correct way of defining argument is, well, it's all those numbers, right? So you cannot just say it's that one number. It has to be all those numbers. So we really want to think of a multivalued function. It's the proper definition of argument is just, all these numbers. And that's actually the right way of doing it. It's not quite a function, like real valued function in the sort of classical sense, but in complex analysis, we're generally fine with multivalued functions. So if you're somewhere on the if you ask on the internet about multivalued functions, there's always some somebody very smart that tells you that no, function is never multivalued. In complex analysis, functions are multivalued quite often, right? We call them multivalued functions, right? So if we just say function, we do mean a single valued function, but there's going to be multivalued functions around. I've already, well, this is one, another one, for example, the square root is another one, or any root is another multivalued function. The logarithm that we'll see is a multivalued function. So these things come about quite often. All right. Now, one last thing is that argument at 0 is undefined. I mean, you could maybe say it's all real numbers, but it's kind of pointless, right? Because it's when you have 0, then r is 0, and then so no matter what you multiply it by, you still get 0. So I guess technically you could say, well, it's all the numbers or none of the numbers or just undefined. It's probably better to just leave it undefined at 0 at the origin. All right, now one way to try to solve this multivaluedness, we'll see sort of more ways to try to do it, because, well, I mean, it is sort of a problem for certain computations. Well, one way to do it, and it's not always the best way to do it, but, well, we try something called the principal branch of the argument. And basically, we pick the theta that's between minus pi and pi. There's only one such argument, because if you add any multiple of 2 pi to it, you get out of that range. So there's for any single complex number, there's one theta that's in that range. You say, well, okay, so why don't we just do that? Well, the problem is that it is discontinuous, right? If I'm on the negative real axis, right, which is basically where theta is pi, well, if I'm going from from the top, right, from the positive in imaginary parts, I'm getting pi, right? And if I'm going from the negative imaginary parts, then I'm getting minus pi, right? So this I get difference of 2 pi out here, right? And it's not a continuous function, right? And here you can also see kind of the problem at 0, right? But this guy is discontinuous on a very large set on the entire negative real line. So it's not not actually as good as you would hope it is, and a lot of times it's actually better to think of the multi-valued argument than the principal branch. Although the principal branch is something that, for example, if you have a computer program that is, has the argument function, it's probably going to be the principal branch that it's giving you, right? Even though, well, I mean, it could give you any other possible argument, right? But a computer needs to give you one number, right? So it has to pick one. Now, another sort of issue is that not all people agree, which branch of the argument is the principal one. So it's fairly common. So this range is fairly common, but another very common range is 0 to 2 pi, which would give you the discontinuity on the positive, positive real axis, right? Basically, the thing would sort of go up out here, and then you would end up 2 pi above here. So one of the issues here is, of course, well, so which is it, right? So you always have to, double check when you're reading some book or some paper if they say principal branch, which principal branch, which one are you referring to, right? Although again, it doesn't actually, in most uses you don't want to actually use the principal branch. So we'll see more of that. Now let's see what the exponential does to the complex plane, just like it's related. So first, if you look at this equation, if you think about it, it actually means that the exponential is never 0, right? Actually, not just this equation. It's this equation and the fact that it's not 0 at that one point. Let's say it's 0. Right? It's at e to the 0 is 1, right? But then this equation will give you that it's not 0 anywhere else. So I'll let you think about that as an exercise. It's very, very quick exercise. So it never takes on 0 value, but it's onto, right? And you can see that from the polar, from the polar decomposition of complex numbers. So the complex exponential, it's onto, but it's not 1 to 1. It is infinitely many to 1. Again, we've seen that. I mean, that's really why the argument is not a well-defined single-valued function, right? Why we had that problem was trying to define the argument. And that's, again, if I take e to the z plus I times any multiple of 2 pi, I get the same number back, right? So, right, so it has, infinitely many different points go to the same point, right? But it is onto. That's not hard to see. Actually, it's not hard to see just by looking at this, right? I can clearly get anything, any complex number, once I know the polar form of it, right? Now, if I look at this, then it also tells us, what it does sort of geometrically, right? So let's first look at, so this includes a bunch of different things, but let's start with a vertical line. Let's suppose this vertical line, right? So that's when x is a fixed constant, c, right? Now, you look at where that goes. If I let x be some constant, then it's e to the c times e to the iy, right? So that line goes to a circle. right? And it actually goes around that circle infinitely many times as y goes from minus infinity to infinity, because the exponential is infinitely, infinite to 1 mapping, right? It basically takes that line and just sort of wraps it around infinitely many times around the circle. Now, that also means that if you take a strip, so in this case, this sort of dark strip, right, and you take it all the way up to infinity, right, then that gets wrapped around this annular region over here. So if I want to, and again, it gets wrapped around infinitely many times, right? So it's not a one-to-one mapping in any way. If you wanted it to be one-to-one, you wouldn't get the whole, right? I mean, you'd have to sort of cut it at some point, right? Again, that probably wouldn't be exactly what you wanted, right? But it takes the vertical strip, it takes it onto an annulus, right? And you can check what the if x is between a and b, then the modulus over here is between e to the a and e to the b, right? Now, if I have a horizontal line, right? If I fix y equals c, and where that goes is a ray from the origin. So it's not a whole line; it's a ray. So it doesn't quite start at the origin because the 0 is not in the image, but it goes. Right, it takes this ray from the origin, not quite including the origin, all the way to infinity. Right, so it sort of maps this horizontal line, gets taken to a ray, right? In basically the y is giving you the angle at which you're going, right? It's giving you which argument you're taking, right? So therefore, if you take a horizontal strip, right, what it goes to is a sector, right? And actually, this guy can be one-to-one as long as the horizontal strip is not too wide, right? If it's not wider than 2 pi, it will actually go one-to-one onto a sector, right? Which between those two angles, right? So in particular, if you take something of width 2 pi, and you have to if you want to make it sort of onto, you have to also add in not just the open strip, but you have to add in one of the boundaries. So maybe let's put the upper boundary, right? But let's start at some 2k pi, so some multiple of pi, and let's go up one further multiple of 2 pi, and let's throw in the upper boundary as well. That guy goes one-to-one onto C, right? It has this sort of the same sort of issues as the argument if I want to think about the inverse, right? So it's not I don't want to really think of it as necessarily a bijective map as being a nice bijective map. It's bijective, but the inverse is not going to be so nice, as we'll see once we get to logarithm. All right, so that's that's good for this current lecture, and next time we'll look at the Riemann sphere, which is basically we add infinity and then see what happens.